All right, so the next reaction, the next addition reaction is going to be halogenation. And so this would be adding, for example, a bromine, meaning diatomic liquid bromine, meaning that you're going to be adding a bromine to both vinyl carbons. Or it could be chlorine, meaning you're going to be adding a chlorine to 2 vinyl carbons. Halogenation is adding a halogen to both of those vinyl carbons. So let's see what this looks like here. These are actually really important reactions for like synthetic chemistry. If we take an alkene and we treat it with chlorine gas, this is my halogenation product. So again, I have my 2 vinyl carbons and I've added a chlorine to each of those vinyl carbons. These turn out to be important for, what am I thinking? Polymer type reactions, because we could take this di-substituted chlorine and then perform an elimination reaction. We get a vinyl carbon here, and then this double bond can play the role of a nucleophile again. And so this creates sort of these polymerized reactions that we see. So PVC, for example, is made from starting with an alkene, performing a halogenation reaction, getting this vinyl chloride, and then reacting vinyl chlorides with themselves. Okay. We'll see why this is in a second, but halogenation, we're going to find, is an anti-addition reaction. So what does that mean? That means that one of those halogens is going to be added to the top. The other one's going to be added to the bottom of this double bond. So in terms of the products that I would expect here, I don't get all 4 possible stereoisomers. I only get the 2 where my 2 bromines are added to opposite sides. Okay, so notice here we have an anti-addition, so one of them's pointed up, one of them's pointed down, and vice versa. I also get the enantiomer pair from that. Okay, so these halogenation reactions are anti-addition reactions. And also we are going to restrict ourselves to just chlorine gas and just bromine. It turns out that iodine is just too slow to perform a halogenation, whereas actually fluorine gas is too good. Usually fluorine is less reactive, but in terms of these halogenation reactions, it's very reactive, which leads to explosive kind of conditions. So only ever focusing on chlorine and bromine. So let's take a look at how these reactions occur. So the first step is your double bond is again playing the role of a nucleophile. Double bonds love doing that. But your bromine, diatomic bromine is behaving a little bit weird because we don't consider bromine to be polar, right? It's a non-polar compound, but it is still quite polarizable, which means that every once in a while, the distribution of electrons will be such that on one side you have this net positive charge, and on the other side you have this net negative charge. And so really how we think about the diatomic bromine is you have a bromine atom that's bonded to a good leaving group, which is in this case the bromide ion. So the first step is your nucleophile comes and attacks that partially positive bromide atom and kicks off that bromide leaving group. Okay, just like always, alkene is acting as that nucleophile, electron donor. Okay, so then why is this an anti-addition? So again, the first step is you have your double bond reaching out and grabbing one of those bromines that kicks off this other one. And so then we have this question of whether it's going to be a syn addition or an anti-addition. All right, we said it's going to be an anti-addition. Let's look more closely at the mechanism to see why this is. Okay. So again, double bond reaches out, grabs that partially positive bromine, kicks off that bromide leaving group. But actually what happens is that this comes down and forms another bond that gives us a cyclic bromonium ion intermediate. All right, bromonium ion. Most importantly, though, another cyclic intermediate. We saw this again with the oxymercuration reactions. These cyclic intermediates make it so that you can't have syn addition All right, I can't have my bromine attacking from this side because it's all blocked up by that cyclic intermediate. So the only thing you're going to see is the anti-addition. Okay, so the full mechanism here would again be first, double bond plays the role of a nucleophile, but then you have this cyclic intermediate, this cyclic bromonium ion intermediate that's formed. And then the bromide that got kicked off as a leaving group in that first step now is playing the role of a nucleophile and attacking that cyclic bromonium ion from the anti-direction. Your book, it's at this point in the chapter, got lazy and started just writing En when there was an enantiomer pair. So that would correspond, I guess we have this like Hawthorne kind of projection to this, right? So you would get both pairs of enantiomers, but again, you could have 4 possible stereoisomers formed, but you're only going to get 2 of them because you have this stereospecificity of the anti-addition. So again, this will influence the number of products that you get. So if we started out with cis-2-butene, and then we had an anti-addition, meaning the bromines went on either side, right? We could get 2 different products that would form. Okay, a pair of enantiomers. This is another instance, just like the hydrogenation reactions, where you're adding the same thing to both vinyl carbons. So you have to be a little bit careful. Again, if I was going to do the trans, I would say, oh, this is an anti-addition, right? But importantly, this is a meso compound. So I would only have 1 product that's formed in this particular reaction. Right, so this is because, again, both of what you're adding to both vinyl carbons is a bromine. So you have the possibility of creating this plane of symmetry. And it's kind of hard to see here, but if I rotated about that single bond, you'd be able to see that this is indeed a meso compound because I have that nice plane of symmetry running through there. Okay, so again, just like the hydrogenation ones, be careful. These are anti-additions, but you still have the possibility of forming a meso. All right, so now let's make our little cheat sheet here. So in terms of mechanism, this is one where I do expect you to be able to draw the reaction mechanisms from scratch. And again, remember you got that cyclic bromonium ion intermediate. In terms of regioselectivity, you don't have anything to worry about there because you're adding bromine to both vinyl carbons. There's no sort of decision of what's going to happen to this. Is it more highly substituted, less highly, blah, blah, blah. Doesn't factor in at all because you're just going to have addition of bromine or both chlorines to those vinyl carbons. The one thing that we do got to remember is in terms of stereoselectivity. Yes, this is an anti-addition. Okay, so these are stereoselective reactions and they are anti-additions.